Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
Hello everyone, welcome to lecture 31 of the course Marine Renewable Energy Systems, Analysis, Design and Development. I am Dr. Basin Patil, Assistant Professor in the Department of Civil Engineering, PDEU, Gandhinagar, Gujarat. In the previous lecture, we discussed linear motion electricity generator and direct drive PTO systems. We understood how linear generators convert wave induced motion directly into electricity through electromagnetic induction, and explored their components and operating principles, also discussed their advantages, challenges and performance considerations. In today's lecture, we will move from power conversion technologies to an equally important aspect of wave energy research, wave basin testing techniques. Before a wave energy converter is deployed in the ocean, its performance, stability, survivability and power generation capability must be carefully evaluated under controlled laboratory conditions. Wave basin provide researchers with a safe, and repeatable environment to study the interaction between waves and marine structures. In this lecture, we will understand the purpose of wave basin testing, learning about different types of wave basins and wave makers, discuss scaling laws and similarity requirements, and understand the instrumentation used for measurements, and explore the procedures adopted for testing wave energy converters under regular and irregular wave conditions. By the end of this lecture, you will have clear understanding of how physical model testing is conducted and why it remains an essential step in the design and validation of marine renewable energy systems. So, let us begin by understanding the role of wave basin testing in wave energy converter deployment. Before discussing wave basin facilities and testing procedure, it is important to understand why physical model testing is still necessary, even though sophisticated numerical simulation tools are available today. Numerical models have become powerful tools for analyzing the wave energy converters and offshore structures. They help us predict hydrodynamic forces, device motions, power capture, and structural responses under a wide range of sea conditions. However, numerical simulations cannot perfectly represent every physical phenomenon occurring in the ocean. For example, non-linear wave effects can be difficult to model accurately, particularly when wave amplitudes become large. Similarly, wave breaking, turbulence generation, and complex viscous effects often require significant simplifications in numerical models. Another challenge is fluid structure interactions. When a floating structure interacts with waves, the response may involve coupled hydrodynamic, mechanical, and structural behaviors that are not always captured completely through simulation alone. In addition, some hydrodynamic phenomena are scale dependent, meaning their behavior may change with geometry, operating conditions, and environmental parameters. Because of these limitations, physical model testing remains an essential part of marine engineering research and development. Wave basin experiments provide a controlled environment where researchers can reproduce ocean conditions and directly observe the behavior of a device. Such experiments are used to validate numerical and analytical models, ensuring that theoretical predictions match actual physical behavior. They also allow engineers to evaluate device performance under controlled wave conditions, measure motions, loads, and power capture, and identify potential design improvements. Wave basin testing is particularly important for investigating survivability under extreme wave events, where safety and structural integrity become critical. Most importantly, experimental testing provides confidence before expensive full-scale deployment in the ocean. Therefore, numerical simulations and physical model testing should not be viewed as competing approaches. Instead, they complement each other. Numerical models help us explore designs efficiently, while wave basin experiments provide the experimental evidence needed to verify those predictions and understand real world hydrodynamic behavior. This is why wave basin testing continues to be a fundamental step in the development of wave energy converters and offshore renewable energy systems. Now that we understand why physical testing is important, let us examine the specific role that wave basin testing plays in the development of wave energy converters. Role of wave basin. Wave basin testing serves as a bridge between numerical predictions and real world hydrodynamic behaviors. It allows researchers to observe how a device actually responds when subjected to a controlled wave conditions. The first major role is hydrodynamic performance assessment. Before evaluating power generation, we must understand how the device interacts with waves. Researchers measure parameters such as response amplitude operators, commonly known as RAOs, which describe how the motion of a structure changes with wave frequency. Wave basin tests also help determine resonance and damping characteristics, both of which strongly influence energy capture performance. The second role is motion and load measurement. A wave energy converter experiences multiple modes of motion including heave, surge, pitch, roll, sway and yaw. During testing, these motions are carefully measured along with mooring forces and structural loads. These measurements help engineers verify that the device can operate safely under expected environmental conditions. The third role is PTO performance evaluation. Once the hydrodynamic behavior is understood, the power takeoff system can be evaluated. Researchers assess power capture efficiency, damping characteristics, and overall energy conversion performance. Wave basin testing is particularly useful for identifying the optimal PTO settings that maximize energy extraction. The fourth role is survivability assessment. A wave energy converter must not only generate power efficiently but also survive extreme storms and severe sea states. Wave basin experiments are therefore conducted under extreme wave conditions to evaluate structural integrity and stability and overall survivability. Finally, wave basin testing plays a crucial role in numerical model validation. Experimental measurements are used to verify and calibrate computational models such as CFD simulations and potential flow analysis. A numerical model that matches experimental observations can then be used with greater confidence for design, optimization and full scale predictions. Therefore, wave basin testing supports every stage of wave energy converter deployment, from understanding hydrodynamic behavior and measuring loads to optimizing power generation and assessing survivability and validating numerical models. In short, it provides the experimental evidence needed to evaluate the performance, reliability and safety of a wave energy system before they are deployed in the ocean. Before conducting any model tests, it is important to understand what a wave basin actually is and why it is such a valuable facility in marine engineering research. A wave basin is a controlled laboratory facility designed to generate and study waves and understand their interaction with offshore, coastal, marine structures under scaled conditions. In simple terms, a wave basin allows engineers to recreate ocean environments inside a laboratory where experiments can be conducted safely, economically, and repeatedly. Let us examine or understand the major components shown in this figure. At the end of the wave basin, we have the wave maker. This system generates regular or irregular waves with specified heights, periods, and spectral characteristics. The generated waves travel across the basin and interact with the test model, which may represent a wave energy converter, or it can be an offshore platform or floating structure or a coastal installation. As the model responds to the incoming waves, several instruments are used to collect data. Wave gauges are installed at different locations to measure wave elevations and monitor the characteristics of the generated wave field. A motion tracking system, often based on cameras or optical sensors, records the motion of the model such as heave, surge, pitch, roll, sway and yaw. All measured information is sent to the data acquisition system where signals are recorded, processed and analyzed. At the opposite end of the wave basin, a wave absorber is installed. Its purpose is to minimize the wave reflections from the basin boundaries. Without absorbers, reflected waves would interfere with the incoming waves and affect the accuracy of measurements. Wave basins offer several important advantages. First, they provide a controlled wave generation, allowing researchers to reproduce specific sea states whenever required. Second, they ensure repeated testing conditions, which is essential for comparing different designs and validating numerical models. The third, they provide extensive instrumentation capability, enabling accurate measurement of waves, motions, forces and power output. Finally, they offer a safe experimental environment where researchers can investigate extreme wave conditions without the risk and costs associated with full scale ocean testing. Therefore, a wave basin serves as a miniature ocean laboratory, providing a controlled and reliable environment for studying marine structures and wave energy converters before real world deployment. An essential component of any wave basin is the wave generator, also known as wave maker. The primary purpose of wave maker is to create controlled waves for experimental studies and represent the ocean environment being studied. By adjusting the motion of the wave maker, researchers can generate regular waves, irregular waves and even directional wave fields. The two most commonly used wave maker types are shown in the slide: the piston type wave maker and the flap type wave maker. Let us first consider the piston type wave maker. In this system, a vertical paddle moves back and forth horizontally, like this, and this oscillatory motion displaces the water. And generates waves that propagate through the wave basin. And piston type wave makers are particularly effective in generating regular and irregular waves and are often used in relatively shallow water experimental facilities. The second type here is the flap type wave maker. Here a hinged flap rotates about a pivot located near the basin of the floor. As the flap oscillates, it pushes and pulls water, generating wave motion. Flap type wave makers are widely used because they can efficiently generate broad range of wave conditions, including directional waves, and that approach a structure from a different angles. In many modern wave basins, multiple flap type paddles are installed side by side. By controlling each paddle independently, researchers can create complex directional sea states that closely resemble actual ocean conditions. Both wave maker types are capable of producing regular and irregular waves, but their selection depends on the basin geometry, water depth, and testing objectives. In practice, flap type systems are commonly preferred for large offshore and wave energy research facilities, while piston types are often used in specialized hydrodynamic laboratories. Regardless of the mechanism used, the objective remains same: to generate repeatable and accurately controlled wave conditions for experimental investigations. Therefore, wave makers form the foundation of wave basin testing, enabling researchers to recreate realistic ocean environments inside a laboratory setting. Until now, we have discussed how waves are generated in a wave basin. However, real ocean waves are not perfectly regular. They consist of many wave components with different heights, periods, and frequencies occurring simultaneously. To represent these irregular sea conditions in laboratory experiments, engineers use wave spectra. A wave spectrum describes how wave energy is distributed across different frequencies instead of defining a single wave height and period. A spectrum provides a statistical representation of an entire sea state. Two of the most commonly used spectra in wave energy research are the Pearson-Moskowitz spectrum, in short PM spectrum, and John-Swap spectrum. The PM spectrum represents fully developed sea conditions. They are situations where wind has acted over the ocean for a sufficiently long duration and distance, allowing waves to reach an equilibrium state. Because of this, the PM spectrum is often used to model mature wind generated seas. The second and more widely used spectrum is the John-Swap spectrum, which stands for Joint North Sea Wave Project. The John-Swap spectrum is an extension of the PM spectrum and was developed to represent fetch limited seas where waves are still developing and have not yet reached a fully developed condition. Compared to the PM spectrum, John-Swap exhibits a sharper spectral peak and generally provides a more realistic representation of ocean waves encountered in practical offshore environmental conditions. This is why John Swap has become the preferred choice in many wave energy converter studies and experimental investigation. Why are wave spectra important? First, they allow irregular ocean waves to be represented statistically in a realistic manner. Second, they define how wave energy is distributed among different frequencies, which directly affects device response and power capture. Third, wave spectra are used by wave makers to generate realistic regular wave conditions inside a wave basin. Finally, they play a crucial role in both performance assessment and numerical model validation, because a wave energy converter must operate under realistic sea states rather than idealized regular waves. Therefore, when conducting experimental testing of wave energy converters, researchers often use spectral uh, descriptions of the sea state, with John Swap spectrum being one of the most widely adopted standards for modern wave energy research. Once the testing objectives have been defined and the target sea states selected, the next step is the preparation of the physical model that will be tested in the wave basin. Physical model preparation is much more than simply constructing a smaller version of the actual device. The objective is to ensure that the model reproduces the hydrodynamic behavior of the full scale prototype as accurately as possible. The first step is the geometric scaling. A suitable scale ratio is selected depending on the size of the facility and the objectives of the experiment. Common scale values are in wave energy testing include 1:20, 1:50, 1:100, etc. At a scale of 1:50, for example, every dimension of the model is 50 times smaller than the corresponding prototype dimension. However, geometric similarity alone is not sufficient. The most important requirement in wave energy testing is Froude similarity. Since wave motion is primarily governed by gravity, the ratio between the inertia and gravitational force must be observed. This is achieved through Froude scaling, which is the most widely used similarity law in wave energy and offshore engineering experiments. Another critical aspect here is mass and inertia distribution. The model must reproduce the center of gravity and moment of inertia of the prototype. If these properties are not represented correctly, the model may exhibit unrealistic motions and inaccurate dynamic responses. Next comes buoyancy and stability. The scaled model must have the correct draft, displacement and restoring forces. These properties determine how the structure floats and responds to the waves. Material selection is also important. Researchers generally use lightweight, rigid and water resistant materials that can accurately represent the geometry while remaining easy to manufacture and handle. Finally, adequate structural rigidity must be ensured. The model should behave as a rigid body during testing Any unwanted structural deformations may alter the measured response and introduce experimental errors. Therefore, successful model preparation requires careful attention not only to geometry but also to scaling laws, mass distribution, buoyancy, stability and structural characteristics also important. The key idea is that the model should reproduce the hydrodynamic behavior of the full scale device rather than merely a being merely being a geometrically scaled replica. Only then can the experimental results be reliably translated to full scale engineering applications. One of the most important concepts in wave basin testing is model scaling. Since testing full scale wave energy converter in a laboratory is usually impossible, engineers construct a smaller model. The challenge is ensuring that the model behaves in the same way as that of actual prototype. For wave energy applications, the most widely used scaling approach is the Froude similarity law. Froude similarity is applied whenever a gravity force dominates fluid motion, which is the case for ocean waves and floating structures, ships and wave energy converters. The governing parameter is the Froude number, Fr, defined as ratio of V over root of G into L, where Fr is the Froude number and V is the characteristic velocity and G is the acceleration due to gravity and L is the characteristic length such as water depth, body length or wavelength or depending on the applications. The Froude number represents the ratio between the inertial effects and the gravitational effects in a fluid system. For dynamic similarity to exist, the Froude number of the model must be equal to the Froude number of the prototype. This requirement ensures that the scaled model reproduces the correct wave behavior and motion characteristics. When Froude similarity is satisfied, several important phenomena are accurately represented. Wave propagation characteristics, floating body motions such as heave, surge and pitch and wave structure interaction processes. For example, if a model is constructed at a scale of 1:50, the dimensions are reduced by a factor of 50 and the corresponding wave periods and velocities must also be scaled according to Froude relationships. This allows engineers to conduct experiments in a laboratory while still predicting the behavior of the full scale system with reasonable accuracy. It is important to note that in wave energy testing, matching Froude similarity is generally more critical than matching Reynolds similarity because gravity driven effects dominate the response. Therefore, Froude scaling forms the foundation of nearly all physical model testing performed for offshore structures and wave energy converters. After preparing the scaled model and applying the correct scaling laws, the next step is establishing the complete experimental setup inside the wave basin. A well designed experimental setup ensures that all important hydrodynamic and performance parameters can be measured accurately. Let us briefly examine the major components. The first component is the scaled wave energy converter model, which represents the full scale prototype under investigation. The objective is to reproduce the dynamic behavior of the actual device as closely as possible. Next is wavemaker, which generates the required wave conditions depending on the test program. It may produce regular waves, irregular waves, or specific C states defined by wave spectra. The model is usually connected to a mooring system. The moorings simulate the station keeping and station keeping characteristics of the real device and provide restoring forces that influence motion responses. Another important component is the power takeoff or PTO mechanism. The PTO represents the energy conversion system that allows researchers to evaluate energy capture, performance and damping effects. To characterize the incoming waves, wave gauges are installed at selected locations in the basin. These instruments measure wave elevations and help determine incident, reflected and transmitted wave characteristics. The motion response of the device is measured using motion sensors. These sensors record the 6 degrees of freedom. The floating structure include surge, sway, heave, roll, pitch and yaw. To quantify the forces, load cells are incorporated into mooring lines or PTO systems. They measure tensions and loads acting on the device during operation. Finally, all measurements are collected through a data acquisition system or DAQ system. The DAQ synchronizes sensor outputs and stores experimental data and enables detailed post-processing and analysis. The accuracy of the entire experiment depends not only on the quality of the instruments but also on proper sensor placement, calibration and alignment of the model within the basin. Therefore, accurate instrumentation is essential for obtaining reliable estimates of hydrodynamic performance, structural loads, PTO behavior and overall energy capture efficiency. Having established the experimental setup, the next important task is measuring how the wave energy converter responds to wave excitation. In wave basin testing, we are interested in both the motion of the device and the loads acting on it. Accurate motion measurement are essential for evaluating the hydrodynamic performance, validating numerical models and assessing energy capture efficiency. Let us first look at the common sensors used in wave energy experiments. A widely used instrument is the motion reference unit, in short MRU. This device combines accelerometers, gyroscopes and magnetometers to measure the complete 6 degrees of freedom, often referred to as 6 DOF motions. An accelerometer measures linear acceleration along one or more axes. From these measurements, researchers can evaluate dynamic responses such as surge, sway and heave accelerations. A gyroscope measures angular velocity about different axes. It provides information on rotational motions including roll rate, pitch rate and yaw rate. For high accuracy measurements, many laboratories also use optical tracking system. These systems employ multiple cameras to track effective markers attached to the model, enabling precise measurement of both displacement and rotation. Now let us examine the 6 degrees of freedom of a floating body. The first 3 are translational. Surge is the forward and backward motion along the longitudinal axis. Sway is the side to side motion along the transverse axis, and heave is the vertical up and down motion caused by wave action. The remaining 3 rotational motions, roll is rotation about the longitudinal axis, pitch is the rotation about the transverse axis, and yaw is the motion about the vertical axis. Together, these 6 motions completely describe the dynamic behavior of a floating wave energy converter. The table shown at the bottom summarizes these motions and their physical interpretation. The lower right figure here illustrates a typical measurement arrangement in a wave basin. Wave gauges measure the incident and reflected waves. The wave energy converter model is equipped with MRUs and accelerometers and gyroscopes and load cells. Optical cameras track the motion of the model, and all sensor outputs are synchronized and recorded through a data acquisition system DAQ for further analysis. By combining these measurements, researchers can accurately quantify hydrodynamic responses, structural loads and PTO performance under different wave conditions. After measuring the hydrodynamic response of the wave energy converter, the next step is evaluating the performance of a power takeoff or PTO system. PTO system is the component responsible for converting mechanical energy extracted from the waves into useful electrical power. Therefore, accurate measurement of PTO parameters is essential for assessing overall efficiency. Let us first examine the key performance parameters that are commonly measured. The first parameter is voltage, which indicates the electrical potential generated by the PTO and helps determine electrical power output. The second parameter is current, which represents the flow of vertical charge and is used to evaluate the amount of electrical energy being generated. Another important parameter is displacement, often denoted by X. This measurement provides information about the PTO stroke length and motion amplitude during operation. We also measure force, which allows us to determine PTO loading and damping forces and energy extraction characteristics. By measuring displacement and force together, researchers can better understand how effectively the PTO interacts with wave induced motions. The next parameter is velocity, which is used to calculate instantaneous mechanical power transferred through the PTO system. Finally, power itself is evaluated as the primary indicator of the energy conversion performance. Now, let us look at the instruments commonly used for these measurements. An LVDT or linear variable differential transformer is widely used to measure displacement and stroke length with high accuracy. A load cell measures forces acting on the PTO and mooring systems. Electrical quantities such as voltage and current are recorded using a multimeter or directly through the DAQ. For rotating components, an encoder can be used to measure rotational speed and angular position. All sensor signals are integrated through a data acquisition system or DAQ, which synchronizes measurements from different instruments and stores them for analysis. In wave energy experiments, synchronized measurements are particularly important because wave elevation, body motion, PTO force and electrical output must be correlated in time to time accurately in time to accurately determine energy conversion efficiency. Therefore, PTO measurement systems from the critical link form the critical link between the hydrodynamic testing and energy performance evaluation. Overall, once all sensors are installed in the wave basin, the next challenge is collecting and managing the large amount of experimental data generated during testing. This is the role of the data acquisition systems, commonly known as DAQ system. As shown in the figure, multiple sensors continuously measure different aspects of experiment. Wave gauges record wave elevation and provide information about incident and reflected waves. LVDTs measures displacement and stroke length of the moving components. Load cells measures forces acting on the PTO system and mooring lines. And motion reference unit MRUs record all the 6 degrees of freedom motions of the floating device. Electrical performance is monitored using voltage sensors and current sensors, which measures the generated electrical output. All these sensors produce analog or digital signals simultaneously during the experiment. The first task of the DAQ system is to collect these signals and synchronize them in time. This synchronization is extremely important because wave elevation, body motion, force measurements and electrical output must correspond to same instant during testing. The acquired data are then transferred to a computer or storage device where they are archived for further processing. The next stage is signal processing. Raw experimental data often contain noise and unwanted disturbances. Therefore, filtering and signaling conditioning techniques are applied to improve data quality. Researchers may also perform frequency domain analysis, spectral analysis and mathematical transformations to extract useful information from the measured signals. Finally, the processed data are used for engineering analysis. From these measurements, we can determine quantities such as response amplitude operators or RAOs, motion characteristics, PTO power output, energy conversion efficiency, wave spectra and overall device performance. Thus, data acquisition system serve as the central nervous system of the experiment, bringing together information from all sensors and transforming raw measurements into meaningful engineering results. Without accurate data acquisitions and synchronization, reliable performance evaluation of a wave energy converter would not be possible. Although wave basin testing is one of the most reliable methods for evaluating wave energy converters, conducting experiment is not without challenges. Several practical challenges must be carefully addressed to ensure that experimental results accurately represents real world behavior. The first challenge is scale effects. In laboratory testing, we typically use scaled models rather than full scale devices, while fraud similarity preserves gravity dominated phenomena. Some effects such as viscosity, turbulence and material behavior may not scale perfectly. As a result, certain differences can exist between model scale and prototype scale performance. Another common issue is wave reflection in the wave basin. When waves reach basin boundaries, part of the wave energy may reflect back toward the model. These reflected waves can interact with incoming waves and distort measurements. To minimize this problem, wave absorbers are installed at the wave boundaries. A third challenge here is sensor noise. All measurement systems contain some level of electronic noise and uncertainty, and wave gauges, motion sensors, load shells and electrical instrumentations may introduce small measurement errors. Proper calibration and signal filtering are therefore essential. The next is mooring interference. In experiments, mooring systems are required to maintain the position of the floating device. However, mooring lines can influence the motion response of the model if they are not designed correctly. Researchers must ensure that mooring arrangement accurately represents the prototype conditions. Another important issue is wave absorption issues. Ideally, wave observers should remove reflected waves completely. In practice, some reflections always remain, particularly during long duration irregular wave tests. These residual reflections can affect the hydrodynamic measurements and power estimates. Because of these challenges, experimental data must always be interpreted carefully. A key requirement of wave basin testing is repeatability. Multiple tests are often performed under identical conditions to verify that results will remain consistent, reproducible. Results increase confidence in the quality and reliability of the experimental data. Therefore, successful wave basin testing requires not only good facilities and instrumentation, but also careful planning, validation, calibration and quality control throughout the experimental program. Before concluding this lecture, let us briefly summarize the advantages and limitations of wave basin testing. Let us begin with advantages. One of the greatest strengths of wave basin testing is that it captures real hydrodynamic behavior. Unlike purely numerical simulations, physical experiments can reproduce complex wave structure interactions, nonlinear response and practical operating conditions. A second advantage is numerical model validation. Experimental data are widely used to verify and calibrate the analytical and CFD and potential flow models, improving confidence in numerical predictions. And another benefit is the highly controlled testing environment. Researchers can generate specific wave conditions and systematically investigate the influence of different design parameters. Wave basin testing also offers excellent repeatability. The same test conditions can be reproduced multiple times, allowing reliable comparison of results and reducing uncertainty. However, wave basin testing also have certain limitations. The first limitation is the cost. Establishing and operating large wave basin facilities require significant investment in infrastructure, instrumentation and maintenance. Second limitation is the presence of scale effects. Although scaling laws such as fraud similarity are applied, some physical phenomena cannot be reproduced perfectly at model scale. Another practical constraint is limited basin size. Laboratory facilities cannot fully replicate the vast dimensions and environmental complexity of real oceans, particularly for very large devices. Finally, experimental campaigns are often time consuming. Model preparation, calibration, testing, data acquisition and analysis require considerable effort and resources. Therefore, modern wave research typically combines numerical simulations and wave basin experiments. Numerical models provide flexibility and efficiency, while physical testing offers the experimental evidence needed for validation and performance assessment. Together, they form a powerful framework for the design and development of reliable wave energy systems. Let us conclude this lecture by reviewing the key points discussed today. We began by understanding the importance of wave basin testing in the development of wave energy converters. While numerical simulations provide physical experiments and provide valuable insights, and physical experiments remain essential for verifying device performance under controlled conditions. When we then discussed how physical model testing helps validate numerical and analytical models, providing confidence in design predictions before full scale deployment. Next, we examined different wave conditions and saw that irregular wave testing better represents ocean environments than regular wave testing. For this reason, spectra such as PM and Johnswap are commonly used in modern wave energy converter experiment. We also learned that instrumentation and proper scaling is critical for experimental accuracy. Correct application of fraud similarity, accurate sensor calibration and reliable data accuracy systems are fundamental to obtaining the meaningful results. Finally, we explored how experimental studies contribute to evaluating hydrodynamic performance, PTO behavior, survivability and energy capture efficiency, thereby improving confidence in the practical deployment of offshore wave energy technologies. In summary, wave basin testing serves as the bridge between theoretical concepts, numerical simulations and real world implementation. It remains one of the most important tools for advancing wave energy research and developing reliable marine renewable energy systems. Thank you for your attention. These are the few selected references. Thank you.